Hello there, as promised, I'm back with example 5. I wanted to show you how we go about doing this problem. It's a little bit more complex than some of the others. What we're looking at is for your job as a Space Corp engineer, you're designing a payload container that needs to fit into a spherically shaped container in the nose of a spacecraft. This container has to be shaped like a right circular cone, and you're tasked with finding the volume of the largest right circular cone that can be inscribed into a sphere. So you can see from the picture right over here that I have a cone inside of the sphere. All right. So let's start with what we want. We're wanting to find the volume of the largest right circular cone. And so here, I'm going to write down what we want. We want a maximum volume, V max, right, because it needs to be the largest of the cone. And I want it to be able to be inscribed into a sphere of radius, having a radius of 4 meters. So what I have is a constraint. I can't have a sphere that has a radius bigger than 4 meters. So I'm going to say my constraint here is that our sphere is equal to 4 meters. Okay, so I'm just going to write that down so I have an idea about that. I really like the picture on this one. It helps a lot to kind of see what we're getting started with. But let's write down to get started, because I know I want to maximize this volume here for my cone. Let's write down the equation for the volume of a cone. I know that V for a cone is equal to 1/3 pi r squared h. Okay, so that's the volume of a cone. What I also know, and if you kind of look at the picture, it helps you, is that if I just do a cutaway of my, let's make this circle first. Almost. See if I can get it to look like a circle. There we go. That's better. Not really. Let's see if I can get it to look like a circle here. Let's do my circle. There we go. All right. I'm going to put my cone inside of it, right? So my cone's going to come down and touch the wall here. It's going to come down, and this side's going to touch the wall over here. And it's kind of going to come around, well, more or less like that. And then I'll make a dotted line in the back, all right? So I have some radius on my cone. It's an R, okay? And I have some overall height on my cone. I'm going to call this H. And so what we see here is, assuming that this is the center of my cone, all right, or I'm sorry, of my sphere. This right here is the center of the sphere. Actually, I'll even change colors to make the center of the sphere. Then I know that this is 4 meters right here, from here in the center all the way over to the edge, all right? I also know that it's 4 meters to any other point from that center. So I know that it's 4 meters from there over here to the edge of my radius, where my radius is going, right? And so what the picture does is it labels the bottom part X and the part going up there Y. I'm going to name it R just because it's a radius, and I'll still leave this one Y. So what I'm going to come out of here saying is that I know that my overall height, that's what this right here is, my overall height, so H is going to be equal to 4 plus Y, okay? Because that's going to be that part that's in red going up toward the top, plus the Y distance, however much further down I go from there, or if Y is negative, it would be further up from there. That would look like a pretty short, stout cone. I can also use, if you think about it, this right here I said was 4, this hypotenuse kind of this bottom triangle that we see right here. I know that because it's a right triangle, I also know that this is a right angle, and so I can use the Pythagorean theorem. I can say that r squared plus y squared equals 4 squared. That means that I can actually find r in terms of y, or y in terms of r. All right. In this particular case, I think given the fact that I already have a y in one term in my height right here, I'm going to go ahead and solve my equation over here for r, so I have r in terms of y, because I want to put my height up in this volume equation. I want to get this volume equation all in terms of just one variable, all right? So let's go about doing that. We're going to try and get r in terms of y. We're going to say that r is equal to the square root of 16 minus y squared, all right? And now what I'm going to do is now I have both my height and my radius in terms of one variable, y, which gives me a really, really good start. I can find my volume. So I'm going to say that v for my cone is equal to 1/3 pi. Instead of writing r squared, I'm going to write the square root of 16 minus y squared. Now that's squared times my height. That's 4 plus y. All right. So now I have everything in terms of just that y term. Alrighty. Okay. That's the volume of my cone. Let's clean this up a little bit. I'm going to say that's equal to 1/3 pi. When I square the square root, I'm just going to have a 16 minus y squared times a 4 plus a y. You see we've got two terms there. Before I actually take the derivative here on this one to find a max, because again, when we want to find a max or a min, I want to take the derivative so I can find critical points. I'm going to say this is 1/3 pi. If I do FOIL on this, what I'm going to get is a 16y minus a 4y squared. Let's see, outers, inners. If I do firsts, I'm going to get a 64 and minus a y cubed. Okay, let's clean that up just, well, I'm going to clean it up just a little bit. I'm going to say it's 1/3 pi times a negative y cubed minus a 4y squared plus a 16y plus a 64. All right. So now what I can do is I can actually look for my critical points. So let's go ahead and look for our critical point. And what I'm going to actually do here real quick is just add a page so that we have enough room if we need it. Okay, so if I want to find my critical points, remember what I'm looking at is for v prime for my cone, my derivative of my cone, I'm going to set it equal to 0. I can also look where it's discontinuous. This particular one is not going to be or undefined, right, for any critical points. So if I take my derivative, v prime of cone, what I'm going to have is the 1/3 pi stays the same. Those are just constants. If I take the derivative of the inner, I'm going to get a negative 3y squared minus an 8y plus a 16. All right, and all of that's going to equal 0. All right, at this point in time, what I'm going to do is I'm actually going to divide both sides by the 1/3 pi because, well, we can say or undefined, so let's deal with that. So the undefined doesn't happen because that's never undefined as a polynomial. Let's take care of the 1/3 pi. What I'm going to do is divide both sides by 1/3 pi. 0 divided by anything is just 0, so I can say negative 3y squared minus an 8y plus a 16 equals 0. All right. So if I go ahead and try to factor this thing, what I'm going to have on my factors, actually let's pull out a negative sign. It's just going to make it, or multiply both sides by a -1. That's even better. -1 over here and a -1 over here. And what I'm going to get then is, I like it when my leading coefficient's positive. So as long as I do the same thing to both sides, I'm good. A 3y squared plus an 8y minus a 16 equals 0. That looks a whole lot easier to deal with. So if I factor that, because my brain's working on it, I get a 3y and a y. If I look at my 16, I'm going to do a -4 and a +4 over here. All right, and that should give you, if you FOIL that, that should give you a 3y squared plus a 12y minus a 4y. That's going to give me my 8y, and then minus the 16. This equals 0. That means if either one of those terms equals 0, it equals 0. So I get a 3y minus 4 equals 0. That would give me a 3y equal to 4, or a y equal to 4/3. My second option is y, let's write it out, plus 4 equals 0. That means y equals negative 4. So let's think about that one for just a second. If y equaled negative 4, I would be saying that the y term right here, it would equal negative 4. It would be way up here. And so what I'm suspecting is that's a minimum where I have a volume of 0, because negative 4 would give me a height of 0. So I'm going to cross that one out and say I'm not going to consider that. Y equals 0 isn't even in my list of what I want to consider. I would have no volume there. So I'm suspecting that I have a maximum there at y equals 4/3. Let's give it a whirl and see. We're going to take a look at a sign chart here real quick. The smallest that my y can be, I'm going to say, is 0, up to and not including 0. I'm going to say 4/3 is right here. And I'm going to say the biggest that it can be is 4. That would give me basically no radius. It would mean that I have a cone that goes all the way down to here. It would have no radius, or almost to here, and it would have a very tiny one and go up. Alrighty? So I'm saying that's the domain or potential domain for this function. If I test this, again, I'm testing v prime for my cone. So I'm popping it back into the equation that's right up here. All right, and I'm just looking for the sign of it. If I look at that, what I find is that between 0 and 4/3, let's say I plug in a 1, I'm going to be positive. If I plug in something a little bit bigger, let's say a 2, I'm going to be negative on my derivative. So that means I'm increasing on this interval right here. I'm decreasing on this interval over here. That means I have a max right here, which is indeed what I'm looking for. So that's very good. All right. Now, that means that I've found what that little y distance is, just what this part right here is, this y, just from here to here. I found that for my overall dimensions. What I wanted to know is what the maximum volume of the cone is. So again, keep an eye on this, because sometimes it'll ask you the volume of the cone, sometimes it will ask you what are the dimensions or something like that. In this particular instance, I just want the volume. Now, for this, I have y, and I actually have the volume of my cone in terms of y. I like this one probably the best. And so I can find the volume of the cone pretty easily just on what I already know. So I'm going to say that if y equals 4/3, and then I knew that v cone equaled 1/3 pi, and then I had a 16 minus y squared. I'm going to move this over, and that's multiplied by a y plus a 4. That was my height there, so let's cordon this off so that we can see it. All right, so I'm using this y equals 4/3 now with my original equation. That's from this one right here is what I'm using. Okay, I'm going to go ahead and sub into this. I'm going to say 1/3 pi times 16 minus 4/3 squared times y. Y is 4/3. I really like the y. Plus 4. Again, that's my height. What I'm going to get there is a 1/3 pi times a 16 minus a 16/9. That's going to give me times a 4/3 plus a 12/3 if I get a common denominator there. Here I'm going to put my 16 into 9ths, so I'm going to have a 1/3 pi. If I multiply 16 by 9/9, what I'm going to get is a 144/9 minus a 16/9. That's ugly. If I put these two together, I'm going to get a 16/3 over here, right? All right, let's do one more line. I'm going to get a 1/3 pi times, if I take the 144 minus 16, I'll get a 125 ninths times a 16/3. We can continue. If we want an exact answer, what we're going to get is a 1/3. Oh, wait, if you multiply all those together, what I'm going to get, let's write the right number, is a 2048 over 81. What I did was multiplied all my numerators together, multiplied all my denominators together, and I leave the pi hanging out there. Okay, so this is my V max, right? And that's going to be in, because it's a volume, meters cubed. If you're looking for the exact answer, this right here is my exact answer. I'm going to leave it in terms of pi. I'm not going to plug in the pi onto my computer or my calculator and find the decimal. If I'm asked for a decimal, let's say I was asked for a decimal, rounded to 2 decimal places or to the hundredths, then I would end up with a 79.43 meters cubed off of this. All right. So that's how you do this problem. It's to me, it's kind of intimidating to set up. Once you set it up, it's really not that bad to take care of it. But again, if you have any questions on it or concerns or anything like that, just let me know. I'm happy to help you out. I hope you have a great day. Bye bye.